Anyone for a bit of physics? What we're doing today is position and average velocity under the umbrella of what we call kinematics. Right, so kinematics is the study of a motion of a particle. That's what we're looking at, motion of a particle. Now, that particle doesn't literally mean like a single particle. This can be like the movement of a body of particles or something like that. But we just talk about one particle moving. There'll be multiple particles moving at the same time, but we're just focusing on one. Now, when we talk about the motion of a particle, the first thing we want to know is where is the particle? And that's what we call its position. And when we talk about position, we're talking about the position of a particle is a specification of its location relative to a reference point. Now, a reference point is this thing here, the origin. And if its position is positive, we say it's to the right of the origin. All right, so here, x being 6.25 means it's 6.25 units to the right of its starting point, or a reference point, I should say, not starting point, reference point. Okay, and if it's negative 8.96, we say it's 8.96 units to the left of the reference point. In this case, x represents what we call the displacement, which is the magnitude of the position of change. All right, so that's what these values here, x represents the magnitude of the position change. So here, 8.96 is the magnitude of the position change of the particle relative to the origin. Now, what we're going to do is vary this up a little bit. Okay, so say for argument's sake, this is me. And what I'm doing is I'm teaching a class. Now in methods, motion is only defined to be in a straight line. So here's me teaching a class, and this is here the origin. So basically what I do is I come into class, put my bag down, fire up the computer, and then go to the origin. This is where I'm going to start. And what I can do is either move to the left or the right. Okay, so that's what happens here. So if I was over here, you would say I'm, say, 6 meters to the left of the origin. If I was over here, moving around, teaching like, really dynamic and all that sort of stuff, moving around the class, over here, it'd be like 7 meters to the right of the origin. Okay, so that's what we're talking about. So in methods, the motion can only be left or right. In methods, I can't move forwards or in a 360 rotation. I'd be just left or right. That's all I'm allowed to do. All right, now what I can do is, so notice that, yeah, x is the displacement. It's how far I am from the reference point. But if we consider position versus time, we can tell a story of the movement of the particle. All right. So what you might notice is that, like, you sort of go to your mate, oh, like, I've just noticed that, have you noticed what Mr. Miller does every time he comes into class? He puts his bag down, right? And then he'll sort of go to this position here and then moves in exactly the same way during the lesson. If you like, every 10 minutes into the lesson, I bet you he's in this position here. 10 minutes in later, he'll be over here. 10 minutes later, he'll be here. Okay, so what we can do is grab this axis here, this x-axis, and what we do is we bring it up to here. So this is the position relative to the reference point, and then we can add a time element to it. So this x, its position, becomes relative to time. And what we can do is then graph the movement or the change in position relative to time. And what that will do is, like I said, tell a story about the movement of the particle. And so what we can see here is this particle here starts at origin. Okay, so this would be like me coming into class and starting at origin. It might be like the middle of the whiteboard. Here's the whiteboard here. I stand in the middle. Okay, and this is where I can move left or right. So what I do here is this indicates that as time increases by the 5th minute or second or whatever this unit of time is, I'm standing 7 meters to the left of the origin, to the right of the origin rather, because that's a positive value. So that would indicate that I've started moving to the right. Okay, so at time 0 or onwards, what I do is I move to the right. And you can see here, what happens here is the rate of change has increased. I've sort of got myself really into something and started trudging. So instead of trudging, I've started walking faster. Okay, so I've got to this point here. All right, so starts at the origin and moves to the, I can spell, the right. Now, what have I done here? I've changed direction. So I've got to here, which is 7 meters to the right of the blackboard, so +7. And I've decided this is as far as I want to go. All right, so now what I'm going to do is head back to the left. So I'm going to say then change direction and move left. Note that I'm still to the right of the origin. Okay, I'm still to the right, but I'm moving left. And I continue to move left until about after 7.2 units of time, I end up back at the origin. Okay, so and move left and continue to do so. So that's what I'm doing. I'm moving to the left, and this graph seems to indicate that I'm continuing to move unless I get to some point down here and then come back, and then what I might do is cut back and forward, back and forward, back and forward, whatever. Okay, so that could continue in some other way that I don't know about. So for what values of t is the particle to the left of the origin? So it's to the left of the origin for t greater than 7.2. These are all the times when the position is to the left of the origin. What values is the particle to the right of the origin? That's going to be for t less than 7.2 and t greater than 0. And we're assuming we're at the origin at t equals 0 exactly, and t equals, and I'm approximating here, 7.2. All right, average velocity. All right, so it's important to understand that velocity is not speed. Okay, so very important. Velocity is not speed. So the average velocity of a particle is the average rate of change in position with respect to time. That's by definition. Okay, now it's position, not distance. So position. So please note that velocity is not change in distance with respect to time. This is speed. Okay, so thus velocity is not the same as speed. So very important, velocity is not speed. All right, and this sums it up. It's a bit morbid, but if you die in the same hospital in which you were born, your average velocity would be 0. Because what's happened over the term of your life is that you've been born, okay, and then you go do all your stuff, you go around the world, you change in position relative to time is big, you come back home, you travel to, I don't know, somewhere in Victoria perhaps, and then come back home, blah, blah, blah. Then you get sick in your 80s, and then you go back to the hospital and you die in that hospital. Okay, now remember, what velocity measures is the change in position relative to time. And if you are born and die in the same hospital, your position at both of those moments would be at position 0, at the origin. Okay, and therefore it would be 0 divided by however many years you live for, which is 0. Okay, so again, very important to note when we're talking about average velocity that we're looking at change in position with respect to time, not change in distance with respect to time. All right, and then you might think, well, what the hell is velocity for then? And I'll explain. All right, so we've got a function s of t equals this. So it's a parabola. So it's just worth having a quick sketch of this, which is s of t equals t 6 take t. So that's going to be 6, 0, and it's inverted. Is there any domain on it? Not really. So it's going to do that. And we're presuming that t is greater than 0 or greater than or equal to 0, but it doesn't have to be, but let's see what happens. Okay, so find the average velocity for the time interval between 0 and 1. So that's going to be the change in position So there's 1 with respect to time. So where is it at 0? So the way we're going to do that is we're going to say average velocity equals f of 1. So whatever f of 1 is, which is going to be 6, take away 1, which is 5. Take away f of 0, so where am I there? Over the time taken to do that, which is 1. So that's going to be 6, what was it, 5? 5 take away 0, which is 5 over 1, which is 5. And we're in seconds and meters. So 5 meters per second is my velocity, or my average velocity between there and there. Okay. All right, find the average velocity between 6 and 8. Okay, so what we're doing is change in position relative to time. Okay, now notice that the gradient is going to be negative. All right, now let's do it. So it's going to be f of 8 take away, not f of, that's bad, s. I go at the year 12s all the time about notation. I've just done the same thing they always do. S of 6 all over 2. So I can't do those in my head, nor have I got the inclination. So define f of x equals 6x take away x squared. F of 8 take away 6, 2, negative 8. That sounds good. Meters per second. All right, now what the sign tells us about the velocity is the direction of motion. That's really important. So this being positive means that it's moving. So if the velocity is positive, that means it's moving to the left, moving to the right rather. So we get a positive velocity, that means I'm moving in this direction here, to the right, okay? Now, negative means I'm moving to the left, okay? It doesn't necessarily mean I am to the left of the origin, it means I'm moving left. So this tells us something about the direction of motion, okay? So this one means, so pos means moving right, okay? So the right of the origin, and negative means moving left. All right, so here is another case where we're talking about velocity and speed. Okay, so suppose you have a circular racetrack that has a circumference of 1,000 meters. The car drives around the track such that it takes 50 seconds for a lap. What we'll do is we'll work out the average velocity. So car starts here, I presume, at the start-finish line. So let's pretend that's what it is, start-finish line, and takes off and goes around the track. All right, so what is the average velocity? It's going to be the change in position relative to time. So we're going to do 1 lap around the track. Okay, so 1,000 meters, all right, and start there. So if it starts there, its position is at the start-finish line. That means its position is 0, and finishes there, its position is 0 as well. So it's going to be 0 plus 0 over the distance. Okay, so that is going to be, so this represents here the change in position relative to time, not 1,000, it's a really slow lap, over 50 seconds. So change in position, so starts at 0, finishes at 0, relative to time, which is 50 seconds. So that's going to be 0 meters per second. Okay, so the velocity in this case here is 0. All right. Now, again, I know that that seems useless to you. You might sort of think, well, why do we need velocity then? Well, again, velocity tells us a little bit about what the particle is doing. Is it moving left or is it moving right? Those there tell us a lot more than speed. But in this case, speed is the one that's important, okay, because I want to know how fast this car moved. All right, so average speed is the distance covered, which is 1,000 meters, and the time it took to do it. And that's meters per second. Okay, so the average speed is 20 meters per second. Average velocity is 0 meters per second. All right, particle is moving in a straight line. It was initially at rest at a point O. Okay, let's call that the origin. So here is the particle. It moves to the right of O with a constant velocity and reaches a point A 15 meters from O after 5 seconds. So 5, 15, okay, join them up. All right, so there it goes. After 5 seconds, it then returns to O. The return trip takes 10 seconds. It stops at O. So 5 to 15, so let's put our dot down here. So 10 seconds from this change of direction. On the one set of axes, draw the position time graph and the velocity time graph for the motion. So this, first of all, is the displacement versus time graph. Now, what we're going to do on the same axes or Cartesian plane, we're going to draw the velocity time graph. So what is its velocity, or what's the particle's velocity in the first 5 seconds? Well, remember, velocity is the change in position with respect to time. So position changes by 15 in 5 seconds. That means it's got a velocity of 3. So here's 1, here's 2, here's 3. And notice that this value here, the velocity, is going to be constant, okay? Because that's what happens here. We've got a constant velocity. The gradient anywhere along this line is going to be 3 all the way along it. So we say that the velocity is 3 all the way along here to here. So it's got a velocity of 3. Now on the return trip, what it's got is a velocity of, so we're doing, how far are we going? 15 in 10, 1.5. So the gradient along this line here is 1.5, and it's also going to be negative. So here's 1, here's 1.5 down here. So I'm going to put a dot here and a dot here. Let's just join them up with that. All right, so why the interest in velocity? Well, again, have a look at what the velocity is. Notice that the velocity here is positive. That means I know that the object is moving to the right of the origin. Notice that the velocity here is negative. That means I know that the object is moving left, okay, to the left. Now, it's on the right of the origin, but it's moving in a left direction. Here, okay, I know it's moving right, and it also happens that it's on the right of the origin as well. All right, instantaneous velocity. Now that's one that's really interesting to us. So remember that the instantaneous rate of change is the gradient of the tangent at a particular point on a function. So if I've got a function here, what we're interested in is the gradient of the tangent, okay? And that's the instantaneous rate of change. That's what the particle is doing at exactly that point in time. All right, so thus the instantaneous velocity is the gradient of the tangent on a position with respect to time graph. That's what we're going to get. So if I get a position v time graph and I get the gradient at exactly that point there, that tells us that the particle's velocity is whatever the gradient is at that point in time. So understanding the relationship between position versus time and velocity versus time graphs can be challenging and takes time. Be patient, keep thinking, and explain the story. And this is literally how I do it. So one way I find that helps me is to run your finger along the position versus time graph and comment on the value of the gradient of the tangent at the point where your finger is, and say it loud. All right, so what I can see here, this red graph here is the position, this dotted graph here is the velocity, okay? And what's happening here is that I have got a situation where my graph here, I've got like a positive, so I'm moving to the right, moving 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 right. And what I decide to do is change position here, okay? And what I do is I start moving left, moving left, moving left, moving left, moving left. Okay, that's what I'm doing here. I'm moving left. And what happens here is note the velocity. Okay, so what happens early on is the velocity starts to increase. Okay, and its highest velocity is here. This is the largest velocity, which matches up with this point here. What that means is, imagine this was like me, kind of like old man Miller running a 100-meter sprint. What I do, just sort of start moving off the line, getting faster, then the big freight train starts going. All right, that's what I've done here. This is like my maximum. Okay, this is, at this point here, this is the highest rate of change of position relative to time. So I'm going like the clappers here, okay? But what I do here is I'm heading into the finish line, I start to slow down, and I do something really weird. I get to the end of the 100-meter sprint, I know that that's 6 meters there, but let's pretend it's 100, and then I decide to go back the other way. Okay, so what I do is I decide to go back the other way, and bloody quickly, I might add. Look at the rate of change there. That is really high. Okay, so I go back really quickly, going back, and at this point here, I'm back where I started. Okay, so here I'm moving to the right. That's heading towards the finish line of the 100-meter sprint, and now I start to move left. Let's have a look at the velocity graph. So what it says is my rate of change is biggest there. Then it starts getting lower and lower and lower. Why is my rate of change getting lower and lower and lower? Because what I'm doing is I'm heading to the finish line and I'm like, for whatever reason, going to hit the finish line and go back the way I came. Wouldn't that be weird, girls? All right, so I get to the finish line here and I get to this point here, okay, and I change direction. That means my velocity at that point when I'm changing direction is 0. Now that makes sense because if I'm changing direction, I can't have a velocity, okay, because I'm going the other way. I can't do that with a velocity. That just doesn't work. All right. And then what I do is I go this way. And again, note that the velocity here is negative when it's below the axis. And that means I'm moving to the left. Okay. This means here I'm moving to the right. These are positive velocities, which sums up what's happening here. I start moving to the right and then I start moving to the left. At this point, I am moving left and I am left of the origin. This point here, I'm moving left and I'm to the right of the origin. All right, so for between 0 less than t less than 5, okay, the velocity is positive. For t equals 5, at exactly that point, the velocity is 0. Okay, and for t greater than 5, the velocity is negative. So again, to reinforce what that means, positive velocity means moving right. It doesn't necessarily mean I am right of the origin, it just means I'm moving to the right direction. Recall, I can move right here. So I could be like, sort of get to the 100-meter sprint and show off a bit in front of you guys, and I'll be like, oh, I'll give you all a head start. So I start way behind the start line down here, and then I take off like the clappers and probably come last by a mile and be really embarrassed. Okay, but I can be moving towards that finish line here and be to the left of the starting point here. So that's also possible. I can move right and be to the left of the origin. Okay, but all a positive velocity says is I'm moving right. Velocity 0 means changing direction. Okay, that was that weird thing I did there where I hit the 100-meter finish line, and instead of holding my hands aloft in the air, what I decided was to go back to where I started. All right, and then to get back to where I started, what I did was went in a left direction, which means that if I get a velocity that's negative, means I'm moving left. Okay. Position of a particle moving in a straight line is given by this function here. Okay, we got the function and we got the velocity function as well that matches. So the corresponding velocity time graph is also shown. So let's have a look. Find the average velocity of the particle for these intervals here. So 3.5 and 4.5. So we want to get that average velocity. So between 3.5, there's 3.5 and there's 4.5 there. So that's going to be that part there. We're going to get the average velocity there. Let's define our function. Define f of x equals x cubed take away 6x squared divide 4.5 take away f of 3.5 over what's that? 1, obviously, 0.25. So that one there is going to be, so average velocity is f of 4.5 take away f of 3.5 over 1, which is 0.25. Let's give a unit. Units per time. Okay, whatever, meters per second or whatever. Okay, now we're going to go 3.9 to 4.1. So 3.9 to 4.1. Basically what we're doing is we're getting closer and closer and closer to the instantaneous velocity at that point. Now I can look at the velocity at that point. The answer is going to be 4. Okay, but let's have a look. So we'll change that to be 3.9, 4.1. I like to do the higher number, take away lower. 4.1, 3.9. Over 0.2. So this time round, we got f of 4.1 take away f of 3.9 over 0.2 equals 0.01. Okay, so we got almost 0. So we've gone from a quarter down to 0. And then let's get in a little closer. So that's going to be 4.01, 3.99. And the difference there is 0.02. And we're even closer So from part A, what's the instantaneous velocity when t is equal to 4? Okay, so we can do this two ways. We can presume that as I get closer and closer and closer to this stationary point, I'm going to guess that the answer is, so what's the instantaneous velocity? Velocity is 0 units per second, whatever the unit is, so units per minute. Right, and I can even jam that into the velocity function. So here's the velocity function here. So define g of x equals 3x squared take away 12x. And if I do g of 4, it confirms that the velocity at this particular time is equal to 0. Okay, so from part A, what is the instantaneous velocity when t is equal to 4 exactly? I'm guessing that the instantaneous velocity is 0 based on what's happening here. And I've just had it confirmed with the velocity function based on the displacement function. For what values of t is the velocity positive, i.e. when am I going to get a positive velocity? All right, so the times I'm going to get a positive velocity is when I've got a positive gradient, okay? And that's going to be from here onwards. All the values here, I've got a positive gradient, okay? And that indicates that I've got a positive velocity. So I'm going to say it's for t greater than 4. Now, does that seem to match up over here? Yes, it does, because look, at t equals 4, we've got a 0 velocity and a positive velocity after that, okay? And it also, recall, means that if I've got a positive velocity, it means my object is moving to the right. For what value of t is the velocity negative? So you can see here that it's between 0 and 4, but you can also see here that I've got a negative gradient from 0 to 4. So we're going to say from 0 less than t less than 4. All right, so there's the rest of chapter 16. Rather long video there, 30 minutes, but how do you sum up kinematics in 10 minutes, 5 minutes? Okay, it's tough stuff. All right, so hope you found that interesting. Go ahead and finish off 16E and get ready for calculus starting up on Monday.